Hello everyone, welcome to DMET 602 Network and Media Lab. This is Dr. Amr Al-Mogi. As this course is a continuation of the Introduction to Communication Networks course in the 5th semester, our goal is still to have a deeper understanding of how packets are delivered from one place to the other. In the Intro to Com Networks course, we have seen two modes of message delivery, which are unicast and broadcast. Unicast is where a packet is sent from one source and delivered to one destination, either in the same network or in different networks. And broadcast is when a message is sent from one source and delivered to all destinations in the same network. And we have studied that you can only broadcast within the same local network. So our goal is still to have a deeper understanding of these two modes of operation. And we will also discuss a third mode of operation or message delivery, which is called multicast. And in multicast, a message is sent from one source and is delivered to a select group of destinations, either in the same network or in a different network. Multicast is similar, for example, to what you would do in podcasting. When you want to listen to a podcast, you have to subscribe to it. And if you subscribe to it, then you will get the content that is being sent. So that is what multicast is basically about. Now, we know that in unicast and broadcast, the source and IP addresses are known. So in unicast, the source address is that of the source, destination is that of the destination. In broadcast, the destination address is all ones, 255.255.255.255. So what can be the destination IP address in multicast? It cannot be the address of a single device because the packet is actually going to a group. And it cannot be the IP address of all the devices because you cannot insert more than one IP address as the destination in the packet header. So what can be the multicast destination IP address? It's actually a special IP address that is chosen from a specific range in the IP address space. So there is a specific range of IP addresses that are reserved for multicasting. You choose one of them, and it's actually the address of the group. So when you want to send a multicast message to a group, you put your source IP address as your own, and the destination IP address is the address of a group. And if you want to receive this packet, then prior to that, you must have registered with the router to tell the router that you are actually going to be a member of this group. And so the router, when it receives a message addressed to that group, it forwards it to all the members of the group. But these are basically the three main modes, main message delivery options or modes. That's what we are going to be studying in depth in this course. So in the Intro to Com Networks course, we have taken a look at the protocol stack, and we have seen different protocols in the protocol stack, and our approach was top to bottom. So we started with the application layer and went all the way down to the data link layer. In this course, we are going to actually take a different approach. We are still actually going with the protocols of the protocol stack, but we are going bottom to top. We're starting with the data link layer, and then we will go into the network layer, and hopefully we will have, if we have time, we'll go into the transport and application layers as well. So the discussion today will start with the data link layer. So from the Intro to Com Networks course, we know that the data link layer is responsible for communications over a single link. It is responsible for all the rules of communication, all the operations that are over a single link. And so if you have a packet that is sent from one source across, for example, many routers to a single destination, there is going to be one or different data link layer protocols that are operating over each link. Okay. And we know that the data link layer adds the data link layer header, which includes the MAC addresses, the source and destination MAC addresses. Okay. First thing we will actually discuss about the data link layer is that it is actually composed of two internal sublayers. One of them is called the logical link control sublayer, or LLC, and the other one is called the media access control sublayer. The LLC sublayer is the one that we are familiar with. It's the one that takes the packet from the network layer with the network layer header, adds to it a data link layer header, and send it to the MAC sublayer. The MAC sublayer, the media access control, that's actually where the MAC address term comes from, is the sort of the traffic police. This is the one that determines who gets to transmit when over a single communication link. So since the data link layer is concerned over what happens over a single link, the MAC sublayer is what actually governs the communication over that link. This feature is available in all data link layers, but its importance varies depending on the communication medium. So if you have a shared communication medium where all the devices are actually sharing the same transmission resource, such as a wireless link, for example. So for example, in a Wi-Fi cell, all the devices are transmitting over the wireless medium. In this case, the media access control sublayer becomes really important because it defines how the devices are going to share the resource, when are they going to send and receive. And in fact, many of the standards that we are familiar with are composed of just the physical layer and the MAC sublayer. So the Wi-Fi standard, IEEE 822.11, is composed of a physical layer and the MAC sublayer, and so is Bluetooth and Ethernet. Now, when you say you have a Wi-Fi router at home, it could be that it has an LLC sublayer and the network sublayer, but this is not an accurate term. So the Wi-Fi access point itself is only composed of a physical layer and the MAC sublayer. Okay, so we will focus today on the medium access control, which controls access to the medium, defines basically which devices gets to send at which time, how do they share the common resource between them. But before we do that, we must look at what the network actually looks like, what are the common topologies of networks. With wide area networks, these are basically the ones that we have most common, either point to point. So you have two routers, for example, as the endpoints of a link. Hub and spoke, where you have one networking device in the middle that is responsible for connecting everyone, or a full mesh topology where everyone is connected to everyone else. This is for the WAN topologies. For the LAN topologies, the classic ones are called bus and ring. Bus is as if you have sort of like a fat cable that is running across an institution, and you plug into this cable with a pin-like structure from your device, and this is how you connect to the network. The ring topology is where devices actually take turns to transmit over the shared medium. These two topologies are outdated. The ones that we have now are the star and extended star. So if you have the star topology, all these devices are connected to each other using a networking device, which is typically a switch. And if you have too many devices for a single switch, then you have more than one switch. You connect the switches together, and the devices are connected to the switches. These are mainly the two topologies that we will see in this course. Okay, so over any of these topologies, the communication is either half duplex or full duplex. If it is half duplex, that means any device can be sending or receiving at any time. The devices cannot actually send and receive at the same time. If it is full duplex, then the devices can actually send and receive at the same time. So in fact, when you have a device connected with an Ethernet cable, this Ethernet cable inside it, you have 4 or 6 or a certain number of twisted pair copper wires. So if you have, for example, 4 twisted pair copper wires, 2 of them will be dedicated to each endpoint of that connection. And so because of that, the devices will be able to send and receive at the same time because each of them has their own dedicated set of copper wires. So they don't interfere with each other's resources, and there will be dedicated hardware to send and receive packets, so they can actually send and receive at the same time. So it's full duplex communication. In most shared resources, the communication is half duplex, meaning that you can either send or receive. So back to the discussion of media access control, we are actually concerned with nodes that operate in half duplex communication, because if they're full duplex, then there is really no resource sharing. So media access control makes sense when nodes operate in half duplex and they need a way to share the resources between them to determine when do they get to send. When did they get to send? This is called contention-based access. Basically, the devices are competing for access to the media, and they need to figure out how a device will actually win the competition and win access to the media. Okay. We will discuss an example, which is a legacy network not found anymore, using a networking device that is called a hub. So a hub is basically a networking device that consists only of a physical layer. All a hub does is that when it receives a packet, it will forward it on all the ports that are connected to the hub, except the one it came from. So in, in figure number 1 here, if PC1 sends a frame, the hub will receive it and will forward it to PC2 and PC3, regardless of who the frame is actually intended to. It's a physical layer device that sort of acts as a receiver, a repeater. Okay, so how can, now what's the problem actually in this setting? Why do we need to regulate access to the medium? Because it's a shared medium. Imagine, for example, PC1 is sending a frame to PC3, and at the same time, PC2 is sending a frame to PC3. So in this case, the hub will receive both frames and will forward it to all the devices. So if a device receives more than one frame simultaneously, even if they're not fully synchronized, if the frames overlap with each other, then the receiver will not be able to differentiate between the frames and all the frames will be lost. A receiver cannot receive more than one frame over the shared resource. So medium access control has the objective of reducing or eliminating completely the collisions. You don't want there to be many collisions in your network. So we have seen how a collision is possible because the hub actually just forwards the packets from all the ports. It may receive packets from two different devices and forwards them, and all the destinations will hear them, and there will be collisions. So what would the devices do in this case? They would do something called carrier sense multiple access. It's basically a way to politely access the medium. It's the same thing that we do when we're standing with a group of friends and we're trying to have a conversation. What we typically do is that we listen before speaking. So we listen to until we find that no one else is speaking, and then we actually start to speak. The devices do that. If they're using carrier sense multiple access, they will listen to the medium, which means that they will open the receiver and try to detect electrical signals on the wire. If they hear anything, then that means that the medium is occupied and someone else is transmitting, and so they will not transmit and they will wait. If they don't hear anything, then they will transmit right away. Now the question here is, how long should they sense the medium for? If they open the receiver and sense the medium, how long should they do it for? If they just do it for a very short period of time, then obviously they may miss a transmission. They just open the receiver and listen, they don't find anyone, and so they start transmitting, and it could be that there is another frame on its way. Because propagation delay over networks is not zero. It takes time for a frame to travel from one device to the other, and if the distance is very large, then it may take actually a lot of time for a frame to travel from one place to the other. So you have to wait for a time that is equal actually to the maximum propagation delay over a network, so that you are more or less fairly certain that after this wait that the medium is free. Because if you don't do that and you start transmitting after a short interval, it could be very possible that another frame is on its way and you just actually didn't hear it. That's actually carrier sense multiple access. Legacy devices do carrier sense multiple access, but they do with it an additional component that is called collision detection. So it's called carrier sense multiple access with collision detection. Collision detection is basically that when a device senses the medium and it detects that it's free and starts transmitting, it will actually continue sensing the medium. It will continue listening to the medium. Basically, while it is sending, it will open its receiver and start listening as well. If it hears that there is another transmission on the medium after it has started sending, then that means that a collision will occur and no need to continue transmitting the packet. Okay, because the packet will actually be lost. There will be a collision and the packet will be lost. And so carrier sense multiple access with collision detection listens to the medium after transmission starts and abandons the transmission in the middle of it if a collision or if another transmission is detected. Wi-Fi devices, basically the ultimate shared resource is the wireless resource. They don't do carrier sense multiple access with collision detection. They do CSMA with collision avoidance. Basically, when a wireless device wants to send something, it still has to sense the medium, but it sends the medium for a relatively constant period of time. Collision avoidance means that after this constant sensing period is over, a device will choose a random number and wait for an additional period to sense the medium during that period as well. So if the constant time is 10 milliseconds, a device will wait for 10 milliseconds, and then let's say it will choose a random number between 1 and 50. And if that number is, let's say, for example, 25, then it will wait for an additional 25 milliseconds before it determines that the medium is free. This figure here shows actually the difference between having collision detection and not having collision detection. In the figure on the left, B starts transmitting first, and you see the transmission goes everywhere. Because it's a wireless transmission, it will go in all directions, and it moves to all devices with time. So for example, at this moment, the transmission will reach C, and at this moment here, the transmission from B will reach D. After a little bit of time, device D will also send at T1, and so as you see here, the transmissions will interfere with each other, and both of them will be lost. With collision detection, which is the figure on the right, after B starts transmitting, okay, once it detects that another transmission is ongoing, it aborts the current transmission. It doesn't continue transmitting. What it would do is that it will wait for a random period of time and start actually sensing the medium again until it finds it's free and then tries retransmit. Okay. Now, even if you do carrier sensing, collisions are not eliminated. Even if you do CSMA with collision avoidance, collisions are not eliminated. Consider actually this scenario. You have devices A and C. Both want to send the packet to device B. And so let's assume that arbitrarily A starts first. So it does carrier sensing. Let's say it will detect that the medium is free and start actually sending to B. After a while, C wants to send to B, and so it does carrier sensing and also starts sending. Now, if we assume that B is within the wireless range of A and C, because the wireless range is fixed, it doesn't, I mean, more or less fixed. It's not a specific constant because it fluctuates, but it has a range. So let's assume that B is within the radio range of A and C, but A and C are too far from each other so that they hear each other's transmission. That means when A sends something, C will not hear it, and when C sends something, A will not hear it. So when A does carrier sensing and sends to B, C will not hear this transmission. And so when C wants to send to B, it will also do carrier sensing, but since it doesn't hear the transmission from A, it will conclude that the medium is free and start sending, causing a collision at B. And you have to be aware that it doesn't matter whether C is intentionally sending to B or not. If C is sending to another device here, for example, B will still hear this transmission because it's a wireless transmission. It goes everywhere. It's called an omnidirectional transmission, which means that the wireless wave travels in all directions. So the transmission from C to any device will interfere with what B is receiving as long as they are using the same frequency, okay, or the same channel. That means that as long as C is sending anything to anyone, there will be a collision at B. This is called the hidden node problem. And it's a hidden node problem because A and C are hidden from each other. Now, Wi-Fi has actually a modification that deals with this problem. Before A will send its packet to B, or before any device will send a packet to any other device, they will start by sending a small frame that is called the RTS, or request to send. This includes the source and destination MAC addresses and includes also the length of the frame that will be sent. Okay, so A will do carrier sensing and then send the RTS. B will receive the RTS. It will do carrier sensing and then send the CTS. When A receives the CTS, it will then send the frame, and then B will send the acknowledgement. Why does this actually help avoid the hidden node problem? When A sends an RTS, B will hear it. When B replies with the CTS, everyone within the range of B will hear it, regardless of who the CTS is actually intended to. As we said, it's a wireless transmission. So when B sends the CTS, both A and C will hear it. So now C has the knowledge that B is about to receive a frame. And so it refrains from the transmission and waits for a later time. So in Wi-Fi, anyone who hears an RTS or CTS packet will refrain from transmitting and wait for a later time. The introduction of RTS and CTS deals with the hidden node problem, but introduces another problem, which is called the exposed node problem, which is shown in the figure in the bottom. So assume that B wants to send a frame to A, and at the same time, C wants to send a frame to D. B can hear A and C, but A and C are too far from each other, and obviously D is too far from B as well. So let's assume that B will start first. It will do carrier sensing, send an RTS to A. A will do carrier sensing, and then send a CTS back to B. Now, the CTS is only heard by B, But the RTS that B sends to A first is heard by both A and C. So when C hears an RTS, it will refrain from transmitting to D, even though the transmission from C to D will not cause a problem because C is too far from A. So the transmission from C will not reach A. And we only care about collisions at the receiving side, not at the sending side, because collisions happen at the receiver. So it doesn't matter that C is interfering with B because B is the sender. The important thing is that E is not interfering with A, which is the case. So the transmission from C to D should have been allowed. But because C heard the RTS from B, it will not transmit and it will wait until a later time. And so this is called the exposed node problem. There is no collision in this case, but it's a wasted transmission opportunity. C should have been allowed to transmit to D, but was not because it heard an RTS. Okay. Second thing we will discuss today. So we discussed how the Wi-Fi standard operates in the data link layer. We will also discuss briefly the Ethernet protocol. It's one of the most widely used protocols in the world. And again, it is composed of a MAC sublayer and a physical layer. It's called 802.3. And because it's one of the oldest protocols that we have in networks, it has had so many versions at the physical layer. So we have versions that support 10 megabits per second and all the way up to 400 gigabits per second. The ones that we have most in deployment are 100 megabits per second, 1 gigabits per second, and 10 gigabits per second. So the devices that we have in our offices are typically connected using 100 or 1 gigabits per second, 100 megabits or 1 gigabits per second. And when you want to connect buildings, you either use 10 gigabits per second or 40 gigabits per second. The higher rates are used for networks that have very large traffic. Okay, and as we said, a header is added that includes the MAC addresses, and in Ethernet, the minimum size fragment is 64 bytes long, and the maximum are 1500 bytes. And this is actually one of the reasons why you would need to do framing at the network layer, because maybe there is a fragment that is sent and it needs to be forwarded, and the MTU is different than 1500 bytes. Okay, we have discussed MAC addresses in the Intro to COM Networks course, so we'll not go into this again. There are basically three types of MAC addresses. The one that we are familiar with is the unicast MAC, and the unicast MAC belongs to a single device. We also discussed the broadcast MAC, which is all ones. So when you want to send a broadcast packet, you insert the all ones destination address, all one destination IP address, and all ones destination MAC address as well. The third type of MAC address that we will discuss is the multicast MAC. So basically, we had discussed multicasting at the beginning of this lecture. So when you have a multicast packet, the destination IP address is that of a group. So what should be the destination MAC address in this case? Basically, if you have the IP address, which is 32 bits, and the MAC address, which is 48 bits, if you want to find out what is the destination MAC, the first 25 bits are 01005E. This is a constant value that indicates that this is a multicast packet. And the remaining 23 bits are important from the rightmost 23 bits in the IP address. So you take the rightmost 23 bits of the multicast group IP address and you put them as the rightmost 23 bits of the multicast MAC address. And this becomes your multicast MAC. Okay. What we want to discuss now are the operations of the switches. So we have discussed switches in Intro to COM networks, and we have said that the switches are data link layer devices that implement only the data link layer and the physical layer, and they forward packets based on the MAC address. So a switch receives a packet and looks up the MAC address table and discovers the MAC address and uses the port that is associated with this entry in the table and forwards the packet accordingly. We had also said that the switch is a plug and play device, so you don't really need to do a lot of configurations for the switch. So now we will actually learn how is it a plug and play device. So because it's a plug and play device and it doesn't really have any routing protocols, it needs to discover the MAC address table on its own. needs to discover how to forward packets on its own. So as an example, let's assume that we have this switch and it's connected to devices A, B, C, and D. Let us number the ports of the switch: 1, 2, 3, 4. So initially, when the switch is switched on, the MAC table is empty. So let's assume that A will send the packet first to X. This will include the MAC address of A as the source MAC. And if it is sent to D, for example, then it will include the destination MAC of D as the destination MAC. Now, the switch receives this packet, and it will look up the MAC address table and find that it's empty. So what it would do in this case is that it will do something called flooding. Mainly, it will send the packet on all the ports that it is connected to, except the one where the packet came from, but not before it makes a note that it has just received the packet from this device A over port 1, and so it concludes that device A is reachable over port 1. Okay. Now, let's assume that because flooding was used, the packet arrives at D, and let's assume that a response is generated from D and going back to A. And so the switch will now receive a packet from D going to A, and so it will look up the table and will know that A is actually connected to port 1 and will forward the packet to A right away, but also not before it makes another entry that D is connected to port 4. As the other devices actually continue transmitting through the switch will populate its MAC address table accordingly. Okay, so that's basically how a switch will learn how to forward packets. It does it on its own, no configuration needed. It learns the MAC addresses eventually. Okay. And last thing we will discuss today is ARP. We have discussed ARP in Intro to COM networks. It's the protocol that is used to discover the MAC address of a device that you already know the IP address of. And we said that ARP can only be used within a local network, so you cannot actually discover the MAC address of a device in a different network. If you want to send a packet outside your local network, you do ARP to discover the MAC address of the default router, and then the default router will forward the packet. Okay. What we will do now is we'll see a short demonstration that basically illustrates some of the concepts that we have discussed in this lecture. To consider this network, you have 6 end devices divided into over 2 subnets, and so there is a router that connects them. That's why you actually see 4 devices with addresses starting 172.16.31 and 2 devices with addresses starting 10.10.10. Okay. These 2 devices here are served by an access point. That's why you see the connection indicated this way, because the access point sends a wireless transmission that reaches everyone. These 2 devices here, 31.2 and 31.3, are connected to a hub, and so it is a physical layer device. Now, let's consider what happens when we try to ping 172.16.31.3. Okay, let's first switch to simulation mode, and we want to make sure okay, let's just bring it back. Okay, let's try this again. So ping 172.16.31.3. We switch to simulation mode, and we want to make sure that ARP is visible. Okay, so if we try to ping, before we actually start the ping, if we want to ping from this device to that device, 31.2 to 31.3, the ICMP packet will be created here, the ping packet, but before it can travel anywhere, 31.2 needs to know the MAC address of 31.3, which is why it will need to do ARP before actually sending the ping. As we see here, the ICMP packet is created. If you click on it, you will see that the IP addresses are already there, but the MAC addresses are not, which is why an ARP packet is created. If you look at the details of the ARP packet, you see that the destination address is all ones, source address is that of 31.2. This is the source IP, and this is the target IP that I want to discover the MAC of. And so the ARP packet is sent to the hub. Now, the hub is the physical layer device. It doesn't have any intelligence. It just actually forwards the packet on all the outgoing ports. So it sends it both to 31.3 and sends it to the switch. 31.3 is the right destination, so it will reply now. And the switch, because it receives an ARP query, the ARP query is a broadcast packet, and so it will send it to all the ports as well. And you see here the switch send it to 31.4 and 31.5 as well as the router. The three of them will discard. 31.3 has replied now to the hub. And if you open the packet, you will see that the ARP reply is no longer broadcast. The destination address is that of 31.2, and this is the source and destination IP addresses. So it is received at the hub. The hub again will forward it over all the outgoing ports, so it reaches the switch and 31.2, and the switch will discard it. And now the MAC address is available at 31.2, and so the ICMP packet can now be sent. And now if we open it, we can see that the MAC addresses also exist, and so now 31.2 is ready to send the ping. So it sends the ping to the hub, and the hub will forward it both to the switch and 31.3. The switch will discard it, 31.3 will receive it, and it will reply back through the hub, and then it goes to 31.2. If we switch to real time, we will see that the 4 packets are delivered at the destination. If we look at the ARP table, so if we do ARP/A, you will see that there is an entry in an ARP table corresponding to the one that has just discovered. Now, let's try to ping another device in a different network, 10.10.10.3, and we switch to simulation. Okay. Now, because we are pinging a packet in a different network, we will not be able to discover the MAC of 10.10.10.3. Instead, we want to discover the MAC actually of the default router. So if we start the process, you will see that an ARP packet is created, and here destination MAC is all ones, source MAC is that of 31.2, source IP is that of 31.2, and destination IP is that of the default router. Even though I'm pinging 10.10.10.3, I cannot discover its MAC. I'm actually discovering the MAC of the default router. So the packet goes to the hub forwards it, switch to router, router now replies, and if we look at the reply of the router, we will see that it is going to 31.2, okay, because it's within the same network. And so eventually the ARP packet goes to the hub, 31.2, and then the ICMP packet can now be sent. It goes to the switch. Now, once the ICMP packet, the ping packet, is received at the router again cannot send it to 10.10.10.3 because it doesn't know its MAC. So it has to do ARP again. And if you see here, the ARP is now trying to discover the target IP, which is 10.10.10.3. So the ARP packet goes to the switch, to the access point, and then to the two end devices. Then the reply comes back to the access point, to the switch, to the router, and then the ICMP packet can actually be sent. Now, if we switch to real time, you will notice that here, the first packet was lost. The remaining packets arrived correctly, the ping packets. If we repeat the ping, you'll find that all 4 ping packets arrived correctly. This is something specific actually to Cisco devices. In the Intro to COM Networks course, we said that the routers do forwarding based on something called the routing table, which contains an IP address and an associated port. Cisco routers contain something called a CEF table, Cisco Expedited Forwarding, which contains layer 3 information, but contains also layer 2 information or MAC addresses. Okay? And so for a route to be used by a Cisco router, it needs both information, which is why when the first ping packet arrived, it was dropped because the layer 2 information was not there. The router needed to do ARP first in order to discover the MAC, and then the ping packet can actually be forwarded. Let's see a different example. Okay, now we have this network. There is no hub. There's actually two routers connected to each other, and these routers serve the 5 end devices that we see here. So if we open this device and we do ping 172.16.31.3, they arrive correctly. Let's try to ping .10.10.3. Again, you will see here that the first packet is lost, as you see, and the remaining ones arrive correctly. And if you ping it again, the 4 packets will actually arrive correctly. If we go to the switch, now if we do ARP/A, you'll find that there are 2 entries, one belonging to 31.3, where I send the first ping, and one belonging to the interface of the default router that is connected to this network, which I discovered because I was sending a packet to another network. If we go to the switch and we open the CLI, okay, and we do show MAC address table, we will see that the switch has already discovered all the MAC addresses and has populated the MAC address table. This is because the switch is monitoring all traffic, and so initially it will do flooding and forward the packets on all the interfaces until it starts reading actually or learning which devices are connected to which port. And so you will see that, for example, this device is connected to port 3, fast Ethernet port 3. This device is connected to port 1, 2, and this device, which is probably the router, is connected to the gigabit interface 1. If we go to the router, we go to CLI, but in the case of the router, we have to go to the privileged exec mode first. So you do enable. Okay. If you do show MAC address table, you will not actually get anything because the router does forwarding based on the routing table, the CEF table. So it doesn't use the MAC address table, and so it doesn't get populated. There is a way to have something like a plugin to the router such that it is able to do forwarding based on MAC addresses as well. And in this case, the MAC address table will be populated automatically, just like a switch. But in most routers, you don't have that. Instead, if you do show IP route, you will see actually the full routing table of the router. There is a legend here that shows you how the route was discovered. So you have D. If you scroll up a little bit, you will find actually the legend. So D is EIGRP. EIGRP is actually a routing protocol. So this means that this route was discovered using EIGRP. Then you have 2 other indications. You have C and L. C is a directly connected network. So C is connected and L is local. Local is something that is in the router itself, and connected means that this is actually a destination that can be reached directly through the interface. So the difference is if you have, for example, 10.0.0.0/8, this is the address of a network that can be reached via 192.168.0.1. That means this network is not reachable directly. You have to forward it through 192.168.0.1. Whereas 192.168.0.0/24 is reachable directly from this particular router. That's actually the difference between these two things. Okay. Now, I'll show you something else. If I do show IP ARP, this is actually the ARP table of the router. It has 2 entries associated with it. Now, obviously, the switch doesn't have an ARP table because the switch doesn't understand IP addresses. And you have to keep in mind that there is an important difference between ARP table and MAC address table. The MAC address table contains the MAC addresses and how to reach them through the physical ports. The ARP table doesn't contain ports. The ARP table contains the IP address and the translation to a MAC address. Okay, so what happens if I do clear ARP cache? This is a command that is supposed to delete all the entries in the ARP table. If you do it at the router and you do show IP ARP, you'll find that the entries are still there. Okay, this is again because of the way Cisco routers do forwarding. As I said, because it's the CEF table, it needs the layer 2 information with it. If you switch to simulation, and I will show you how this is done. So note what happens when I do clear ARP cache. Once you do clear ARP cache intending to delete these entries, you'll see that the router automatically generates an ARP packet to rediscover these addresses. So clear ARP cache doesn't really work on a Cisco router because it needs to maintain the layer 2 or MAC address information in the CEF table itself. So it automatically tries to rediscover the MAC addresses. That's it for today's lecture. We'll see you next time.